Hello, welcome back. So, we have reviewed last lecture, we have discussed second order hyperbolic and then method of characteristics for first order hyperbolic. Okay. So, let us see there are some finite difference methods as well for first order hyperbolic PDEs, both scalar as well as a system of equations that can be represented in terms of a vector equation. Okay. So, let us discuss the following methods. So, to start with explicit scheme. Okay. So, we consider equals to 0. So, sometimes we take a constant a, but in this case a is 1. So, maybe we can write this, then okay. So, now if we go for forward and for both, what we get minus h, okay, or plus equals to 0. So, now from this u I j minus lambda u I plus 1 j, we get this, and this is of order k, this is of order h. So, clearly where lambda is k by h. Okay. So, this is explicit. However, you can see to compute at j plus 1 require jth level only 2 points I and I plus 1. So, this is an important observation. Okay. So, this appears like this. To compute I j plus 1, it asks I j and I plus 1 j. So, it does not ask this point. Okay. So, this is an important observation, right. So, now let us try to see the stability aspects of this. So, we have u I j plus 1 okay. So, then let u p q equals to okay. So, if we substitute in the above equation, we get zeta power p plus 1. So, I am writing the simplified one. So, zeta power p get cancelled throughout. So, we get zeta 1 plus lambda minus lambda, we have I plus 1. So, we get one excess here. Okay. So, this can be simplified as okay. Now, mod square is okay. So, this can be simplified as where theta is beta h by 2, but we can observe, see this is positive. So, this is greater than 1 and hence unstable always. Okay. So, there is a suitable explanation for this behavior. So, what is happening in this method, as I mentioned, this is an important observation. To compute the value at this point, it is asking only these points. Okay. So, that means, if the initial data is changed here, so then this is getting affected. However, if there are some changes here, then this is not realizing. Okay. So, this can be explained suitably, this can be explained suitably via Friedrich-Levy condition. So, this is popularly known as CFL condition, Courant Friedrich-Levy. Okay. So, now what is this states? So, this discusses about such unstable behavior. Okay. So, let a first order hyperbolic PDE be approximated by a difference scheme okay. Then so this is A, B, C. Okay. So, then so this is I j. Okay. So, therefore, this will be, call it P. So, this is I j plus 1. Okay. So, that means U p depends on U a, U b and U c, okay, which are the mesh points. Now, let us say the characteristic curve through P meets AC at D. Okay. So, this is initial line and let us say so the characteristic curve through P meets AC at D. Okay. So, then what happens? As I mentioned, changes in initial values along AC reflects in the value of u p. Okay. So, if you change, right, but unfortunately, if you consider the point D, so this is our P and D, so this is I j, right. So, these changes will not be reflected on u p, which is the solution that depends on D. Okay. You see, when we change the initial data, P is getting affected, but if you compute along the characteristic the solution u p, so we have u p and u p. So, this is computed along the characteristic, but that does not know what is happening at A B C. So, therefore, u p cannot converge to u p as h goes to 0, k goes to 0. So, now what should happen? If any changes in this, they are percolated to P. So, which means since we are computing the solution along the characteristic, the changes which are done A to C must be plugged in at a point D. So, this is possible only when D lies beyond this, that means within this range. If D is any point, so then what would happen? The following is going to happen. If you consider so, this is a P. So, this is our explicit method, right. However, so this is via characteristic. So, now if D lies, suppose you take D. So, then what will happen? Any changes on the initial data, D also gets changed and those changes are percolated to P. So, accordingly the solution capital U P also responds. So, therefore, convergence is possible only when D lies between A and C. Okay. So, when we talked about the earlier explicit method, you can see this point depends on only on these 2 points. So, therefore, if you compute along the characteristic, so definitely it is not going to converge, hence we got instability, hence this is unstable. Okay. So, therefore, what is the remedy? Okay. So, definitely we have to think of some remedy. So, the remedy is forward in time backward in space. So, consider this. So, you can see this is what we have, so backward, right. So, now this implies so we get this. So, this scheme is using the points as follows. So, this is using so I j plus 1 is I j and I minus 1 j. Okay. So, therefore, what would happen? Any changes here. So, along characteristic within this, okay, we can get convergence. So, let us verify this. Let u p q is okay. So, then when we substitute the above equation, we get so we get this. So, this is almost similar, but there is a sign change, and considering the maximum value, okay. So, therefore, less than 1 for lambda less than 1. So, this is stable for okay. So, this is the corresponding stability condition. So, this can be also explained via a CFL condition, because what is inferred using CFL condition, this is P and this is D. Okay. So, what is inferred for convergence? Slope of P D is greater than or equals to slope of P A. So, that is slope of P D is nothing but, see, this is d t by 1 dx by A, from where we are getting okay. So, that is 1 over A greater than or equals to k by h. So, that implies lambda A is less than or equals to 1. So, this is there is a coincidence, okay. A is 1 okay, in this analysis. So, therefore, we have corresponding stability condition. Okay. So, CFL condition helps, because if you take any characteristic point which is not on the initial interval. So, what is happening? The changes are not being percolated. So, whereas if you consider D within the range of the initial strip, then initial line segment, then the changes are being percolated, hence we get convergence. Okay. So, let us take an example and do the numerical calculation. Okay. So, this is a problem, and h 1 by 4 . So, comparing with the standard form, we have A equals to 5. Now, we require couple of quantities. So, the quantities we require A plus lambda, A minus lambda, etcetera. Okay. So, let us, if we discretize the corresponding equation, we get so if we discretize this equation, then we get okay. So, let us assume for the time being such a method we are doing. So, then we need various quantities A lambda is 5 by 2, then 1 plus A lambda is 7 by 2, A square lambda square is 25 by 4, then 1 minus A square lambda square. So, this is minus 21 by 4. Okay. So, now the derivation of this method, I will do it okay. So, I put a remark. So, for the time being, you think we are solving this problem which has been approximated by this scheme. Okay. So, then star for lambda equals to half is given by u I j plus 1 and A equals to 5. For these values, this is given by 35 by 8 . Okay. So, it is given by this. So, now we have to compute at various grid points. So, we compute at various grid points. So, consider j equals to 0 So, then at first time level then we have 0 t equals to 1 plus 2 t. So, this implies is 1 plus 2 j k, which is 1 plus j by 4. Okay. Because k is 1 over 8, then u of x 0 is u I 0 So, now so on. So, consider I equals to 1. So, then u 1 1 is 35 by 8, u 0 0 So, u 0 0. So, j is 0. So, this is 1 and u 1 0 from here 2 minus x 1. So, that would be 2 0 is 2 minus x 2. Okay. Now, suppose I equals to 2. So, this 1 0 So, one can compute. So, I 0 1 2 3 so on so forth. So, now let us go for j 1, then we get from this formula when j is 1 we get u I 2 1 plus okay. So, now I 1 So, this will be u 0 1 then u 1 1 just now we have computed minus 2 u 2 1 also we have computed. So, we get some number. Okay. So, that means we can keep on computing j 1 j 2. You can see we have computed u 1 1 u 2 1, then we could go for u 1 2. Okay. So, one can compute the values like this. However, I made a remark, this equation can be approximated by this, right. So, let us see what kind of approximation gives this method. Okay. So, this is called Lax-Van explicit method. So, what we are doing, consider constant. So, now we would like to get an explicit approximation for this. So, Taylor expansion of u I j plus 1. So, you consider this but notice from 1 accordingly okay. So, therefore, u I j plus 1. So, we have this u I j minus, we are substituting this a k and for this okay. So, we have this. So, now going for central difference approximations, we have for this term, then the next term so second order plus dot dot. So, this implies so we can adjust so this is our Lax-Van explicit method. So, we have made use of a small trick. What is that? We have considered the straight away we have considered the expansion at u I j plus 1. However, we made use of the equation and transferred the time derivatives to spatial derivatives and approximated by central. Then we got explicit expression that involves all the 3 points. Okay. So, now exercise show that the error involved in the above approximation is okay. So, this can be shown. So, now let us talk about stability of this method. Formula or method, whatever. Uij minus so we have considered a equals to 1. So, this is considered in raw form without adjusting. So, then let so this implies so this is sin square beta h. So, this is 1 minus 4 So, therefore, one can less than or equals to 1 for okay. So, this also tells that Lac's explicit method is stable for these values of lambda, which are coinciding with the earlier method which we have described. We have considered forward time and then backward space. So, and then obtained a corresponding method. So, that method and also this both are stable for the same range of lambda. So, now as I mentioned at the beginning of this lecture, the corresponding first order hyperbolic equations can be extended to a system of hyperbolic equations. So, let us see how the system look like. So, we have so we consider okay. So, then we have the corresponding system can be put it in this form. So, for example, say we have okay. So, this can be put it in the system where A dou u by dou x. So, this is our A, then so this is matrix A. Okay. So, such kind of system can be also be discussed. So, now when we have such system, how do we approximate without going over the individual components? Okay. So, we follow similar method as we have done for a single equation. So, we consider then of course, of I j. So, this is, so we make use of the equation, then so this implies again we go for central, so this is Van der for a system. Okay. So, now let us consider the general case where the equation is in more standard form. So, if this is in the standard form, then we get again we make use of this. So, dou u by dou t we substitute minus, okay. Now, consider this this will be, again we substitute, so minus so now we have an interesting quantity, which one? So this is nothing but our A of u, which is the Jacobian, okay, of f with respect to u bar. So now the method becomes, so therefore is so now we go for central difference approximations. So this would be so this I am doing for the completion sake, otherwise if you consider a specific example and try to do this, then you would understand much better. You see, for this central would involve midpoints. Okay. So, you may refer any book on numerical analysis. So, where midpoints so this is the case for a system. Okay. However, this is very abstract, unless you consider a system and then try to follow the notations, and maybe if you write a code, so then one would feel more confident. So, let us see a simple system and see how it looks like. So, this can be expressed as follows. So, this implies so where so accordingly we can use our this. Now, let V I j plus 1 W I j plus 1 approximate okay, let them be approximating this. So, then from the above structure we get the following. Okay. So, each component wise I just would like to give you an idea, and similarly okay. So, if you consider such a system, making use of the approximation for this system in a general notation, we get each component and one can solve them. Okay. So, this is a simple example. However, if you take a real numerical example where you have coupled hyperbolic systems, it would be better to write a code and implement, so that one can understand better. So, with this we have almost covered topics in PDE. For example, we started with the parabolic type, where we discussed explicit and implicit methods for parabolic PDEs, in particular with respect to heat conduction equation, and then we moved to elliptic, where we discussed about Laplace and Poisson, and then we moved to hyperbolic, where we considered wave equation in case of second order, and in case of first order hyperbolic we discussed scalar equations as well as systems. Okay. So, this course main idea of this course is to get exposed to various finite difference approximations to both ODEs and PDEs. So, in case of ODEs, as you know, we started with single step methods and then multi step methods, and then we have also gone for finite difference methods for boundary value problems. So, you get some idea to start with, then once you are done with this course, you can definitely understand advanced techniques. So, for example, alternate directions and then maybe higher dimensions and staggered grid and things like that. Okay. And of course, finite elements. So, we have almost come to an end of this course. So, we have one lecture left, and then we will discuss maybe some summary and maybe some important directions. Until then, bye.